Welcome. Today we'll begin taking a look at neural networks. Specifically, we'll look at the multi-layer perceptron, which is the plain vanilla version of a neural network. The core idea of neural networks is learned composition. We're going to build up a model as a composition of simpler models, and then we're going to train the whole composition jointly. You can think of this as another way of combining models, like bagging subsets the training data and takes an average or plurality vote of the resulting trained models. Or gradient boosting fits residuals so that we can add models together to get a single output. Neural networks work by taking the output of one model as the input of the next model. And the key point is that we're going to take the training data and use it to adjust the parameter values of each model together. So you can think of this as like supercharged feature engineering. Rather than putting our features directly into a model, we think to ourselves, well, probably we could rearrange those features somehow to make them more useful to this model, but maybe we don't know how to do that. So we give it to the machine to do. We take another model and put it in between and get that model to produce a refactoring of the features that's going to be useful to the last model that produces the output. And maybe that's not giving the model enough leverage either. So what we can do is put still another model in between. And if that's not enough, we could add still another model. So let's look at the results for a particular example. We're going to approach this sort of backwards, starting with a visualization of the final output and seeing how that model is actually trained in a few lines of code, and then finally unpacking it down to the basic details. So consider a classification problem where we have red points and blue points. And these points are going to be separated reasonably well visually. We can tell as a human how to draw a curve that separates red from blue. And because the data are not heavily overlapping, we're going to be able to reliably tell blue points apart from red points. So suppose for simplicity we want to separate these points with a hyperplane, which in the two-dimensional setting means a line. Clearly there's no way to do that, but what we can imagine doing is applying a map to these points to take all of them to a higher dimensional space where maybe there would be a separating plane. And we've actually already seen one way to do this. So problem 1 asks us exactly that. What technique have we learned that would enable us to linearly separate these classes? And the answer is the support vector machine with a kernel. If we choose a kernel, that specifies implicitly a map from this space into another space where hopefully the data will more easily separate. And in fact, that will be the case here if we use a radial basis kernel with a sufficiently small value of gamma. However, this technique is limited because we have to choose the kernel ourselves as the machine learning engineer. We could maybe try experimenting with some different kernels, but it would be really nice just to be able to say to the machine, you learn this map into this higher dimensional space as well. So I want you to learn the separating plane, but I also want you to learn a map which separates these data. So we'll see how to do that with the neural network, specifically by mapping these data into 3 dimensions. And this is one example of the sort of thing that can happen. You end up with the points wrapped around the unit cube, many of the points sort of along this back wall of the cube, and then many points along the top. And from this point of view, we can see that the data separate along a plane. So we can put a plane through here that separates the red from blue points. So if, for example, we map each point to its signed distance from that hyperplane, we would get the points to split along the real number line. What's actually shown here is something a bit different from that. We're mapping to the interval from 0 to 1, and the value is supposed to represent a confidence that the particular point is blue or red. So points which are very far on the blue side would end up here very close to 1, and these points that are very far on the red side would end up close to 0, and points that are a bit more in the neutral zone will end up closer to a half. And we'll talk in more detail later about how to achieve this map that takes us to the interval from 0 to 1. So once we have this whole composition, we can visualize what's going on in each intermediate picture. So we start with this unit interval, and everything from 1/2 down will paint red, and everything from 1/2 up will paint blue. And then we can take a pre-image of the interval under the map from this middle space. And what we find is this top and back edge of the unit cube where the points are, it's split along this particular line. So this line is the intersection of the plane that we're using to split with this surface in 3-dimensional space where the points are. And then we can pull that back to the original picture and see in the given feature space which feature values will get predicted to be red according to this model and which feature values are predicted as blue. So what maps specifically are we going to use for our neural network? Well, at a high level in this picture, what we want to do is start with a 2-dimensional input, and then produce a 3-dimensional value in the unit cube, and then finally produce a vector with 2 components which are positive and add up to 1, whose components we can interpret to mean the probability of being red or the probability of being blue. And then ideally, all of the training data that were blue would map to values which are very small in the first component and large in the second component, and all of the red training points would map to values that are large in the first component and small in the second component. And perhaps the simplest way to imagine mapping inputs to outputs is just to use a linear transformation for each layer. So our first map we might call A1, and it has some matrix W and length 3 vector B, such that each x coming in maps to W1 times x plus B1. And then likewise for A2. There are a few problems with this approach. The most basic one is that composing linear maps just gives another linear map. So we're not getting any leverage out of our composition when we do this. The other issue is that there's no reason for these final outputs to add up to 1, so we'll need to insert something to fix that as well. The first thing we'll do to inject some nonlinearity into the mix is follow the map A1 with a simple nonlinear map. And in order to get the points into the unit cube, as we saw in the picture, that map is going to be the sigmoid function. The next thing we'll do to make sure that the components are positive and sum to 1 is to take the output of A2 and exponentiate each component, which will make every component positive, and then just divide by the sum. And that will make the components of the result sum to 1. Then we'll be able to tell our training algorithm to adjust these values of W's and B's so as to get the first components large for the red training observations and get the second components large for the blue training observations. So let's take a look at how this works in code using a package. There are going to be parts here that we may not be in a position to understand yet, but I want to emphasize how simple it can be as a practitioner to use a neural network on a particular problem. So we're pulling in this neural net script, which just defines the data for us. And we can see it here with the feature matrix X being 2 by 1000. So this is transposed from how you usually see it, but the observations correspond to columns and the features correspond to rows. And then the response values are also a bit different than what you might have seen. Each column here is 1 hot encoded. That just means there's a 1 in the correct position and zeros elsewhere. Since there are just 2 options here, red and blue, it's just 1, 0 if it's red and 0, 1 if it's blue. If there were more options, you would still see 1, 1 and all rest zeros, just indicating which class that particular training observation belongs to. So for example, when we see 0, 1 here, that's telling us that -2, 0.3 is a blue observation. So to build our model, we use this function called chain, which just builds a composition. And chain takes as arguments the individual models that it composes. So the first one is going to be what's called a dense layer. And that's just another term for this linear transformation we discussed, W1 plus B, together with an activation. So this component-wise function that we apply right after applying our linear transformation is called an activation, and we'll include that as well in the dense layer. So we're saying we want a dense layer from R2 to R3. So that's going to set up a 3 by 2 matrix W, which maps from R2 to R3, as well as a length 3 vector B. So together they form the linear transformation, which maps X to WX plus B. And it also is going to follow that with a sigmoid activation. So each component of the output is going to get sigmoided before it gets passed on to the next layer. And initially, these parameters are going to just be random. And once we supply some data, they're going to adjust to try to conform to that data and produce outputs that are aligned with that data. Next, we get a dense layer, this time with no activation, that just takes us from R3 back to R2. So this is going to be outputting a vector in R2, and it's common practice to not have an activation on the last dense layer. So up to the dense layer, you do want activations, providing some nonlinearity between each 2 consecutive linear maps. But for the last one, we usually don't include it. And then finally, we have a softmax, which just takes the outputs from the previous layer, exponentiates them, and makes sure they sum to 1. We also need to say what our loss function is. So this is going to be the thing that the gradient descent algorithm is trying to minimize. And in this case, we're going to use cross-entropy loss. So that's just another term for the loss function we used for logistic regression. So if the model says the red probability is 0.2, and it's actually a red training point, then we'll get a penalty of log of 1 over 0.2. So it's just rewarding the model for being confidently correct and penalizing it for being incorrect, especially if it's overconfident. So then we'll set up our data set to feed into the trainer. And here we're just saying we're going to make 60,000 runs through these training observations. And we'll choose as our optimizer something called ADAM. This is a variant of gradient descent that's very common to use for training neural networks. And we'll talk about some of its distinctions with ordinary gradient descent later. And finally, we just call train on this model. We specify the loss function that we're trying to minimize. We tell the training algorithm which parameters it's allowed to manipulate, which we can conveniently extract from the model just with this params function. We tell it the data set to use to train and the optimizer to use. And this does take several seconds to run. It's doing quite a bit of work, and it's not unusual at all to use neural networks which take dozens of minutes to train, even up to many hours or even days or weeks for really large-scale industrial applications. And finally, we can visualize the results. So we just map x comma y to the output of the model for that x comma y pair. And then we have to use this tracker.data function because the model output is actually not a plain number. It's what's called a tracked number, which is just another name for dual number, because to facilitate training, it's helpful to keep up with the actual values, but also the gradients in each position. And this is what we see. It does a pretty nice job of separating red from blue. And just to show what I was alluding to earlier, if we just look at the output for the first layer, so we plug in this particular point 0, 0, which by the way in the picture you can tell is very squarely red. It's right in the middle of this red clump. Then we get this value, 0.84, and then almost 1, and then 0.02. So what's happening here is the linear transformation is sending this value to something that's quite large, and then the sigmoid comes along and maps that to something very close to 1. And what you'll see if you look at all of the different training observations is that one of these components is going to be really close to either 0 or 1. So that's why you end up with points along the back wall of that unit cube and then along the top. And then if we see what happens after we plug in the first two layers, we get this value, negative 18, 19. And as we said, this value is negative and these don't sum to 1. So then we apply softmax, we pick up this third layer, and that takes us to the interval from 0 to 1 and makes sure that these values actually do sum to 1. And notice here that the scientific notation is using the letter F rather than the customary letter E. And that's a convention associated with the type of the number. So if it's a 32-bit float, then we use F, and if it's a 64-bit float, then we use E. And the reason we use 32-bit floats when we do deep learning is that it turns out to be really important for performance reasons to be able to train these things on a graphics processing unit, which is the thing that renders the graphics when you play a video game. And graphics processing units are designed to handle float 32s, not float 64s. So let's look at a concrete example just to make sure we have a grip on what this looks like mathematically. We're going to use a ReLU activation function, which just takes a number and maxes it with 0, which means if the number is positive, it returns that number, and if it's negative, it just returns 0. So we're supposing in this example we have an input of -2, -4. And the first thing to do is apply the function a1 to that. Next, we apply the activation k, which eliminates any negatives. And then finally, we apply a2. So in problem 3, we're asked to come up with another visualization for this alternating composition of linear functions and activations. So here, W1 is a 2 by 2 matrix, so our initial input is in R2, and then the output is also going to be in R2. And then W is a 1 by 2 matrix, so that takes us back to R1. And the conventional way of visualizing this is with a diagram involving arrows and dots, and those dots are called neurons. So we start with the two input neurons. These are going to be containing the components of the initial input vector. And then we'll draw another column of dots for the output of the first layer, which in this case has two components. And then finally we draw a third column for the output of the second layer. So our first map is A1 and our second map is A2. And the activation function K isn't really available in this picture. So what we usually do is expand these middle two dots into pills. And the idea is we'll put the pre-activation value on the left and the post-activation value on the right. Then we'll draw in all the edges connecting the neurons of one layer with the neurons of the next layer. These arrows correspond to entries of the weight matrix. For example, this bottom one is the bottom right entry of the weight matrix since it connects component 2 to component 2. Another way to draw this diagram is vector-oriented, where we package each column into a single vector and just draw a node for that column. This gives us a little more space to include other values in the picture. Lastly, in problem 4, we're going to try to get a feel for how to manipulate the entries of W and B to try to make a neural net function match a particular function. So we'll take this simple polynomial function, x plus y squared, and its heat map looks like this. We're showing some of the contour lines, The function is its smallest here, and then it grows and it's larger up in the bottom right and top right corners. And we want to try to make this neural net function do the same thing. And here it's quite different. It's low in the top left corner and gets larger towards the bottom right corner. And we get to manipulate the A and B values. Note that these A's actually should have been W's for consistency with the notation above. So this is worth experimenting a bit. But what you can see if you play around with it for a while is that it's quite hard to get it to be good. So here we managed to get a couple of different creases. And notice that these creases are coming in where the values coming into the ReLU are 0. Because then points slightly on one side or the other side are experiencing different linear behavior. But the only nonlinearity comes from the ReLU, and that introduces creases between which the function is piecewise linear. So we're definitely not going to be able to get these curves like this no matter what. The best thing we can hope is to use these creases to do the best job we can at matching up with this function. So what I want to do is skip straight to an example that a student in class came up with, which is to set A1 to be 3, -4, 4, 4, A2 to be 1, 1, B1 to be 1, 4, and B2 to be 2. So if we set these values, it actually looks pretty good. We're starting to get this orange color along the right edge, blue along the left in the middle, and yellow sort of curling around a bit in between. We still have these creases, but they're helping us kind of create contour lines that do broadly the correct thing. But in any case, the main takeaway is that it's quite tricky to manipulate the values of a neural network directly in order to get it to behave according to a specific function. And this is even before we consider that we'll actually only have training observations. Here, the target function is given to us in a really simple form, and ideally we'd like to be able to come up with this fit from training data rather than from knowing the full function itself. So in summary, the core idea is that neural networks are trainable compositions of simpler models. We'll start with some basic building blocks, and then we'll use the output of one as the input of the next one. And then we're going to train the whole composition jointly on the training data. The building block for an MLP, or a multilayer perceptron, is a linear map of the form Wx plus b composed with a component-wise activation function. For example, ReLU, which takes a max with 0, or the sigmoid function, which maps x to 1 over 1 plus e to the minus x. Finally, to train a neural network, we identify a loss function, which says how well the model fits the training data. And then we repeatedly nudge the parameters, which are the entries of the w's and the b's, in whichever direction makes the loss value go down most swiftly.